Okay, so to kind of summarize and recap, enzymes are helping to speed up chemical reactions by providing a low energy pathway to products. Okay, and they provide that low energy pathway by creating a favorable geometry, or we might say improving collision geometry. So if we look at this particular potential energy diagram here for this generic reaction, so that's what this is called here. This is a potential energy diagram. And so here we've got one for a endergonic and one for an exergonic, which we'll look at in a second. But what we need to understand is that these particles A and B, all right, if they're going to form these new products over here, well, they must collide. And when they do collide, all right, so if we have molecule A colliding with molecule B, they have to collide with sufficient energy in order to, they have to collide with sufficient energy to achieve a successful collision. And that minimum energy required for a successful reaction is what we call EA, or energy of activation. Okay, and energy of activation is abbreviated as EA, is the minimum potential energy required to achieve a successful collision, to achieve a successful collision. Sorry, I spelled that wrong, 1L. Okay, and so this molecule that forms in this collision, we call this actually the activated complex. The activated complex. And it is a high energy, unstable molecule, all right, that has the potential to go on to form products. So what we need to understand is it's kind of like our hill analogy. These reacting molecules, yes, they have a certain potential energy, but they're also moving around, right? They're in motion. And so if they collide with enough kinetic energy that it forces this activated complex with enough potential energy, meaning putting enough stress and strain on those bonds, right, that you have a successful collision. So every single chemical reaction has to achieve a certain energy of activation. Doesn't matter whether it's endergonic. So here, the system has to put energy in to achieve this activated complex. Well, every system has to put energy in to achieve this activated complex. And then where you end up in the aftermath is going to determine whether the reaction was endergonic or exergonic. So in this case, the products ended up higher than the reactants. So overall energy had to have been put in, but the energy required to achieve a successful reaction, we call that the energy of activation. And I've drawn that one incorrectly here, so hang on one second. So on this one, the energy of activation goes from where the reactants are to where they need to get to. So this represents the energy of activation in this endergonic reaction. Over here, the reactants are here, and they need to get to here. So the energy of activation here is much smaller, okay? And because the products end up lower in energy than the reactants, well, this is an exergonic reaction, which we talked about before. That means that energy has been released, right? Energy is given off. Regardless, endergonic, exergonic, there still needs to be a minimum energy of activation to achieve the activated complex and a successful collision. So how do enzymes play a role in this potential energy diagram? Well, remember, what enzymes do is they provide a lower energy pathway by creating a more favorable geometry. So if we were to draw in what this potential energy diagram would look like with a catalyst, we would see it looks something like this. And so we can see this is significantly lower than this. So the energy of activation for the catalyzed, and we'd say here in brackets catalyzed, is much lower. And because it's much lower, you're going to have more molecules that are going to have, there's a greater percentage of successful collisions. And therefore, the greater percentage of successful collisions, the rate goes up. In the same way that these other three things influenced reaction rates, it's all about the percentage of successful collisions. Whether you're increasing the forcefulness or how many times they collide, or providing a more favorable geometry and a lower energy. Either scenario creates a greater number of successful collisions, a greater percentage, and ultimately a faster reaction rate. So we can look down here. Maybe you could try pause the video, see if you can fill in the blanks. I'll give you a second and then restart the video. Okay, so yeah, enzymes lower the energy of activation. The EA for any given reaction by helping molecules to align with the correct collision geometry. Okay, this means that they need less kinetic energy to achieve that potential energy of the activated complex. They can collide with less speed or forcefulness. And yeah, you can again maybe use that analogy of putting an electric motor onto your bike to go up the hill, right? The electromotor being the catalyst, so you don't have to work as hard going up the hill. Just down at the bottom here, just to look at some pictures, much like the video showed, we need to understand, we learned back in chapter 3 that proteins are built from amino acids, and they have 4 levels of structure. Remember, primary, secondary, tertiary, quaternary. But it's the tertiary and the quaternary that dictate the shape. Well, we can go back and say, yes, the primary structure, the sequence of amino acids, will eventually lead to the final 3D shape. And that shape is unique to every enzyme. And what happens, much like in the video, when an enzyme binds onto the substrate, it does so at a location called the active site. So this is a uniquely shaped region of the enzyme where the substrate binds. Okay, and so sometimes the substrate might be just one molecule. And when the molecule binds with the enzyme forces, some sort of conformational change to break the substrate apart to produce products. Or like in the scenario over here, this is maybe another example of one molecule, but we could have this reaction going in this direction just as easily, where this enzyme is binding both of these molecules in order to create a favorable collision. So it can be one substrate, 2 substrates, but the active site is unique to the shape of the substrate. One enzyme, one substrate. So you'll often see textbooks refer to the analogy of a lock and key to reflect the nature of the interaction between enzyme and its substrate. So, just like every door has a unique shaped lock to fit a specific key, right? The lock, the shape of that lock being the enzyme, and the key being the substrate that fits into that. There is a sequence of steps to any enzyme catalyzed reaction. And these are described here below. So you have the stage, we can look up up above here. So I'll just letter these in the same way as it's shown here. You've got A, enzyme with active site empty. So that's up here. Then substrate binds to the active site by weak bonds, but it is quickly held firmly in place by an induced fit. So here we have substrate binding in. So remember, these are groups of amino acids, much like in the video, playing a role to bind that molecule in a certain way, interactions between R groups on amino acids and various atoms on the substrate itself. This binding into the active site creates a weakened bond that is often, remember, hydrolyzed. So when we break bonds apart, breaking of things in chemical reactions we refer to as catabolism, breaking things apart, and specifically in the case of most metabolic reactions in our cells are hydrolysis, so water being added. So here we can see water being added across the bond to help break that bond. And then finally, so we have here C, and then finally products are released and enzyme is available to react again. And so the enzyme is returned to its original state. And as it said in the video, this is a huge advantage. The cell doesn't have to manufacture one enzyme per reaction. It can manufacture an enzyme that could catalyze 50, 100, 1,000 of the same reaction. Now, that doesn't mean that it just simply produces one enzyme per reaction. A cell could still produce thousands of the same enzyme, each of those enzymes catalyzing thousands of reactions at a time. And you can see how the rates of chemical reactions will increase with the use of enzymes in our cells. That's it. We'll wrap things up tomorrow and go through the last little bit of notes and answer any questions. We can go over stuff that you have.